So, welcome everybody back. So we left off last time with talking about the connection between the diameter and the radius. And so you don't need to, like, please do not sit down and try and memorize either one of these. Like, you only need to know one of them. You only need to know one. Yes. It's still at my friend's house. It's still at my friend's house. Say what? Thank you. They're very, very pretty. It's my wife's water bottle, actually. So I'm using it basically as they're parent friends, and so we're trying to like leave our sweatshirt over there, essentially claiming them as our friends. But not in actuality. I just keep forgetting it there. But yes, that is my new water bottle. Until I will embrace the flowers. Where were we? There we go. Okay, so just to show you how to use this situation, I would just recommend, honestly, learning this one right here. And then you can, if you're given the diameter, all you need to do is divide by 2. You don't even need to memorize this formula if you just know that the diameter is twice the radius. So example, part 1 is, what is the radius if the diameter is 1,000 feet? And we'll just answer it right off the bat. We won't do a solution because it's a very quick problem. 500. Yeah, and you can, if you want to just do that in your head or in your calculator, you don't need to write down any math to do it. But here, D is equal to 2R. And the fact is, we don't know what R is, but we do know what D is. D is 1,000. So 1,000 equals 2R. And we're going to divide both sides by 2 to get the R by itself. And get that R is equal to 500 feet. That's if you want to do it by pure math. But if you want to do it in your head or on just in your calculus, quick calculation, please feel free to do so. And then 2 is, if the radius is 13 millimeters, what is the diameter? 26 is exactly right. You just double the radius and you got the diameter. But if you want to do it mathematically, so D is equal to 2R. We don't know what D is. That's what we're being asked to find. The radius is given to us as 13. So this is D is equal to 2 times 13, which would be 26 millimeters. Now, an observation that you can test this out at home. It's not really something that we're observing in this class, but whatever. The ratio between the circumference and the diameter of a circle is constant. So the ratio between the circumference and the diameter of any circle that you're given, no matter the size, like we could take my beautiful flower bottle, calculate the diameter, and then calculate the circumference, and then take the ratio of it. I guarantee you'll get a number. And then take a smaller circle or a larger circle, and then a cylindrical object, and then test that. I guarantee you every single time you will get the exact same number. So I have a couple examples here that I decided to do at home. So we're going to say the object, it's going to be a little chart here. Nope. Object is here. Then the circumference. And then the diameter. And then the ratio. So I measured a baseball. And the circumference of a baseball, so if I was to cut it in half, not like so yes, technically speaking, a baseball is a sphere, not a circle, right? But if you were to go along the one of the what are they called? The orbits, the median lines or whatever they are, you get 229 millimeters, and the diameter is 73 millimeters to my best estimates. And so if I do 229 divided by 73, I get 3.137. And then I decided to look at a dinner plate. And I had 31.4 inches here in circumference, and the diameter was 10 inches. It was a 10-inch plate. So 31.4 divided by 10, so 3.14. So not exactly the same, but like it's very hard to get exactly the right measurement. Like not everything, but it's the same number roughly. We're off by 0.003. And this will be true everywhere. If you measure anything that's a circle and you take its circumference and divide it by its diameter, you will always get this number. And this number is called pi. And P, not PIE, but PI for the Greek letter pi. So the Greek letter, 2 lines and then a little squiggle on the top. So pi is one of your first introductions to an irrational number. It is 3.141596939 on and on and on forever. That's why you never want to talk to pi, because they'll just go on and on forever. Ha ha ha. They also just keep talking in circles. Ha ha ha. But thank you. Pi is one of the one of the most important numbers. I like the number E more for like it's a very important number in calculus and beyond. But pi is found in a lot of things, and it has a lot of very interesting properties. There's a lot of weird summations that end up just working out to be pi. For example, if you are to take 1 and then add 1/3 and then subtract 1/5 and then add 1/7, subtract, don't write this down, by the way, don't write this down. But if you were to keep doing this, is it this one? Wait, no, it's just it's adding them all up. If you add up all the odd fractions on and on and on and on and on forever, you'll start to see that this number is pi, which is bonkers. To me at least. There's many other things. If I remember, this is in the deep recesses of my brain, but I believe this infinite amount, if you just keep doing this on and on and on forever, it ends up being pi, which is pretty miraculous. This weird number that is an irrational number. And so just I think I've said it out loud, but I don't think I've ever really explicitly stated it. An irrational number is a number that has a non-terminating, non-repeating decimal answer. So this pi will never ever stop going on. It'll be a number that we cannot write out fully, and it will just keep adding things. And there's no repetition. There's no like point where you can say, aha, that's where it repeats. It just keeps going on and randomizing. There was like a cool guy who could actually calculate it like a savant. That could just calculate those things. It was pretty cool. But I'm just getting on a sidetrack of a history lesson. Fun stuff. For us, we'll use the approximation that pi is roughly 3.14. So for all your homeworks, quizzes, and exams, you're going to use 3.14 whenever pi is going to be used. Just to, this was a design of the course to make sure that if you didn't want to purchase a calculator that had pi, that you could use just 3.14 and get everything correct, instead of having to write down 80 million digits of pi. So the reason why I'm introducing that is because those things are used in the area and perimeter formulas. Area and perimeter. So the area of a circle A is equal to pi r squared. The area of a circle is pi times the radius squared. So the joke that I got throughout my childhood was, well, pi are not squared, pi are round. Cornbread are square. And so that was the joke. Like even when I was in grad school, it was still the same joke. That's the dad's job though. So perimeter of a circle is that P, or in this case, we usually write C instead of perimeter because perimeter usually requires sides and circle doesn't have any sides. It has one continuous side. But C is equal to 2 pi r or pi d. Because right, two radiuses would be a diameter. So you can memorize it either way. This is the more acceptable, 2 pi r. But pi d can be used. So as an example, find the area and circumference of part A will be a circle with radius 24 centimeters. And B will be a circle with diameter 104 meters. Why not? The part A. So your radius R is 24. So then then the rest of it is just using the formulas. So we're going to plug in R is 24 into both of those formulas. So the area is pi r squared. So this would be 3.14 because we're going to use this as our approximation. We're not going to use pi. And then 24 squared, which should be, if you plug that into your calculator, 3.14 times 24 squared should be 1808. 1808.64 centimeters squared, because this is an area. So areas are two-dimensional, centimeters squared. And then circumference would be 2 pi r, which we're going to do 2 times 3.14 times that 24. That should be 150.72. And this is a measurement of distance, so it's just going to be centimeters, not area is a measurement, area is a two-dimensional measurement, circumference and perimeter, that's a one-dimensional. So that's why it's centimeters, just centimeters, not centimeters squared. For the second one, the diameter is equal to 104, which means that the radius is 104 divided by 2. It's half the diameter. So that should be 52 meters. So then from there, we're just going to plug them into the formula. Area equals pi r squared. So that's going to be 3.14 times 52 squared. Get 8,490.56 meters squared. And then our circumference is 2 pi r. So that's going to be 2 times 3.14 times 52. So 2 times 3.14 times 52. 326.56 meters. Any questions on using those formulas? Yeah, because I want to spend most of the time from this section. So on the next thing, which is far more fun, in my opinion, which are composite figures. Composite figures, which are, so definition, a composite figure is a shape that is made up from other smaller shapes, or is composed, rather, other smaller shapes. Hence the name. It's a composite, so a composition of shapes. Now, it's best to see it in a picture representation of what I'm talking about. You've seen composite figures everywhere. You see composite figures more often than you see nice normal shapes. So picture representation. So I want you to draw something like this. That's a composite figure, because it's a figure that's made up. If I were to like, and sadly, you're going to have to copy this and paste it. No. Oh. I give myself a little bit of space. So what we could do, like there are many different ways we could view this. We could view this, and this is the way I have it decided, as 3 small rectangles. Okay, fine. You're gonna do it that way. Okay. So. Okay. We're gonna play it. Let's get you leveled. Okay, there we go. This will make it work. So you can think of it as 3 different rectangles. This first one. And you can think of it as small one right here. And then last but not least is this one. And that is just one way to do it. You could have, and you don't need to draw this one. I don't want to make you draw more than you need to. You could have just as easily broke it into this piece, and then a piece at the bottom, and then a piece right here too. That would be another way to write the exact same thing. And the reason why I'm color coding it is how would we figure out the area of this shape? Well, it would be to break it up into into several pieces of shapes that we do know the area formulas for, because there's no area formula for that first shape. So the area of this figure is equal to the area of the blue rectangle, or the green rectangle, plus the area of the red rectangle, plus the area of the blue rectangle. Now that's one way to think about it, but there's another way to have calculated the area. We could also think about it as looking at a bigger shape that encompasses that and subtracting off the stuff that it's missing. So I'm going to show you another example, but I'm going to let you finish drawing that. That's a lot of color coding. So. But we can also think of composite figures as a bigger shape with pieces cut out. I'll show you what I mean once you write that down. Two different ways to approach a very, very similar problem. So I could this is an example of a composite figure. Right? Because there's no, that's not a normal shape. That's not a rectangle, anything like that, but we can break it up into rectangles. But what we could also do is we could just make a bigger rectangle. Let's see here. 6. And just snip out this bottom piece. So you could take the bigger rectangle, find the area of that. So area of the big rectangle minus the area of the small rectangle that's been cut out. So there's two different ways to find the same thing. You could do it with the original one that I drew, the one up top. You could just make a bigger rectangle and find the area of what was missing and then subtract that off from the big area. However you want to do it is fine. There's no wrong way to do it. But the fact is, sometimes we have to be a little bit clever when we're given these problems. I've always liked these ones because there's a lot of hidden measurements that you have to figure out just by knowing some facts about the shape in question. Is it okay if are we still drawing? So, example. Find the area and perimeter of part A is going to be kind of a, and this is not drawn to scale, to be clear. That one. And then the measurements that are given is 4 centimeters, 15 centimeters, and then 8 centimeters here. Oh, and then 6 centimeters at the top. And then part B, just draw right next to it. This shape here. And it says 2 feet, 5 feet, and 5 feet. That's all that's given. That's a lot to draw, so I'm going to take a step. Okay. So for part A, I'm gonna bring it down. We're gonna take care of this one. So John Doe student says, "Oh, I got this. I got this." So I'm writing this in red because this is not correct. John Doe student says, "Okay, perimeter. I'll just add 4 plus 15 plus 8 plus 6, and that's going to be 19. That's 33 centimeters. Why does John Doe get it wrong?"
There's a whole side of
Exactly. There's 2 sides that were not listed
there's two.
that we're not given the measurements for. So what is the measurement of this side? Four. How did you get it?
Side. The other 4 that's already there, yeah, right, half of it.
Yes, exactly right. So this side, so because these things are perpendicular to each other, and this kind of forms a rectangle, not kind of, it does. This side length is 8 centimeters. This side is 4 centimeters. So this has to add up. When you add this green plus this, it should add up to 8. So this is going to be, another way to say it would be, this is 8 minus 4, which is 4 centimeters. And by a similar justification, that one should be 9 because it's going to be 6 minus 15. Or 15 minus 6, excuse me. So the perimeter is adding up all the side lengths. And so you can start with whichever one. I recommend going in kind of a clockwise or counterclockwise. Just make sure you're systematic about it. So I'm going to start with the red and then just move my way along in a clockwise fashion. So 9 plus 4 plus 6 plus 8 plus 15 plus 4, which is going to be 46, right? 46 centimeters. Now, why am I being very pedantic about that? Like particular? I still can, I mess these up as well, just purely by forgetting to add a side length. So one thing you can do is you can probably, like, if you find that happening to you a couple times during your homework or whatever, you can kind of just check them off as you go through, or highlight them. as you're going through, like you could go, okay, I've done this side, then I've done this side, this side, and this side. Just to avoid having to get the wrong answer, even though you're really, really close. That being said, so on homework and quizzes and exams and stuff, if you get it wrong, it's going to give you a 0 on that problem. But if you had just made a minor error, you can definitely email me and I can look into it. Ideally, send a picture of your work and I can give you some, if not most of the partial credit back. So that's the perimeter. And so there are two ways we could think about splitting this up. We could either split it up vertically like this into 2 pieces, or we could do it like this and cut it into 2 pieces, or we could do it in 3 pieces if we really wanted to go bonanza and do like that. Do you guys have any druthers? Any preference? The first one. All right, so we're going to split up this way to find the area. So we have something that is 9 by 4, not 15 by 4. Remember, this bottom one is going to be, it looks like it's 4 by 15, but that's the measurement of this entire side. So it's going to be just 9 there. It's a common mistake that students will make. And then the other one, eight by 6. So the area, the total area is the area of the first rectangle plus the area of the second rectangle, the vertical one and the horizontal one. So that's going to be length times width. So 4 times 9 plus 6 times 8, which is going to be 30, 4 times 9 plus 84 centimeters squared. Any questions on that? And this is, oh, go ahead.
Needed the bottom one of 9, the other one was also 9. Oh, no, we only need 7, so I got it.
You got it. Yeah. We don't need to write the other measurements because they're going to be the exact same. Yes. So this actually is far more applicable like to the real world. Like I remember I had to replace the carpet at one point, and they're using pretty much every room that you live in is a composite figure. When you boil it down, like including like the carpet, like the closets and everything, it's not usually perfectly square. So this is something that you can actually use a lot. Have you ever wondered how they give you the price quotes? You get that cool little laser thing that that I got for my for Father's Day. So now I can be a man, that like measuring thing. Just put it here and say it's going to be 16 feet to that wall. So very, very fun. Highly recommend it. It's a very, very fun tool. But this one here, this one's a little more fun. I like this one a lot. Because there's a couple ways we could break this down. Problem though, what's that top measurement? It's not there. Wait, was it supposed to be given? It's supposed to sorry that my notes cut off when I printed them off from my iPad. I think it's definitely needed. It's definitely needed. This is supposed to be 9 feet up top. Sorry about that. Otherwise, this is a very hard problem to solve. Sorry about that. 9 feet. Okay. My apologies. My apologies. But there's one missing side length. And how would I figure that one out? Triangle. Very, very good. Very good. You can inscribe a little baby triangle here. So, well, that gives us two of the measurements, right? Because if this has to be, this whole distance is 5, then the pink vertical distance has to be 3, right? And by similar argument, the base dimension should be 4 feet, right? But that doesn't give me the measurement. That only gave me the arbitrary measurements that I created. The Pythagorean theorem. Yay. So, gonna bust it out. Bust out the Pythagorean theorem. Three squared plus 4 squared is equal to c squared, because that's the hypotenuse. Along the side, that's 9 plus 16, that's 25 is equal to c squared, which implies that c is equal to 5. So this distance is 5 feet. So now we have all the side lengths needed to find the perimeter. We'll just add them all up. There's going to be 1, 2, 3, 4, 5 numbers in total. So when we're adding this up, we should have 5 numbers. Perimeter is going to be 9 plus 5 plus 5 plus 5 plus 2. That's 5 numbers, right? Yes. So that should equal 15, 24, 26 feet. And please feel free to use your calculator. And then for area, there are several different ways we could go about finding it. One such way, the way that first appeared to me, since I've already created this little triangle to create a full rectangle, I'll find the area of the full rectangle and subtract off that little triangle. That would be my thought. But you could also, if you really wanted to, you could, let's use red here. You could break this up into a rectangle and a trapezoid. If you guys remember your trapezoid area formula, which of course, that's a really it's a really common one. We use it all the time. So that's one way you could do it, or you could even break it up into that and add the 2 rectangles and then the third triangle. But I think out of all those options, finding the very, very large triangle and then subtracting off find the very large rectangle and subtracting off the triangle would be the best option. So the area, it used to be, just to complain for just a second, it used to be that you could change whether it's dashed, dotted, or solid or whatever, right on the same page where all your colors were. So I'm still in mourning. Area of the big rectangle minus the area of the little triangle. Area of the rectangle is length times width. So that'll be 9 times 5. And the area of a triangle is 1/2 the base times the height. So 1/2 the base is 4, the height is 3. That's 45 minus 6. So that should be 39 feet squared. Any questions on that? We had to bust out our Pythagorean theorem, or we could do anything. Okay. So I don't know if you guys have looked at the course schedule in a hot minute, but next week is our first exam week. And it'll cover all of Unit 1, and that's it. And then if you look at the calendar on Monday, it says that we're going to have a Unit 1 bring it all together. So that day is meant to be some catch up if we don't get through all of the material for today. And then otherwise, it's going to be meant to be just taking all the things that we've learned and trying to find problems that involve all of the things. So I'm pretty excited for that. I've got a couple of cool problems to do. So if we have time, oh yes, go ahead.
Is our exam like in class or at home?
It's at home. It's at home at your own leisure. Just like with the quizzes, I give you 3 attempts. Best score is the one that's kept. So if you're unhappy with your first attempt, study up, see what you did wrong. And that's twofold, as we talked about at the very beginning of the semester. The fact is, it could be that you just entered. I've had it happen several times already where a student meant to put in 209 or 219, but they wrote 29. So it's like their answer was 29.32 and the answer was 209.32. And so full credit back on that. That's just a typo. So by looking back over your exam, you can find out if you made any typos or if there's any simple things that could be fixed. And you'll find out any mistakes that you made, and then you can study up, take it again, and know fully well that your best score is the one that I'm going to record. So even if you do worse on the second attempt or the third attempt, it doesn't mean that's the score. Yes.
Is the exam also timed like the tests?
Yes, like the quizzes, it is timed. And it's a few more questions. I think it's about 10, I think, off the top of my head. But I can't remember off the top of my head. Yes.
For the exam, if we do retake it, is it the exact same questions as the initial, or is it different numbers?
The numbers are randomly generated. So. I guess my whole point of getting on that sidetrack was to say that I'm going to save some of the fun like application problems with this type of stuff for Monday, unless we have time at the end here. But because I want to make sure we get through this. So section 1.6, which is boxes and cylinders. So now we're going 3D. On 3D. Do you know we only see in 2 dimensions? We are 3-dimensional beings and we can only see in 2 dimensions. Yes, because right now, sorry, what was the name? Angel. You don't have legs based on my picture. You don't have legs. I can imagine that you do based on my experience in the world that you have legs, but I cannot see them because they're hidden behind the desk. If I could see in 3 dimensions, I could see what you ate today. So because I would be able to see all of your body, like all the way through the tube, the human tube that we are, or just a tube. But so we're going to be going to 3 dimensions, which the world we live in. Okay, so box. Box is a container with 6 sides that are rectangles. By definition, is a container with 6 sides that are all rectangles with opposite sides having same dimensions. Having the same dimensions. And then I want to talk about just kind of the different names of the parts of a box. And in case you've never had to draw a box, it's actually quite fun. Start off with just a rectangle. And then what we do with that rectangle is we add 3 lines. Stemming out from it that are all the same dimension, the same distance. And then from there, Then we just connect the lines that we just made. And then if we want to add depth, we have to add a little dashed line to say that these are not actually side lengths that we can see, they're in the background. Boom, we've drawn a box. Always fun to draw boxes, at least in my opinion. I love drawing boxes. That's probably why I am a math major. Just like drawing the shapes. But face. A face is one side of the box. So there's 6 total. So if I were to draw that box again, I'm just going to highlight in this front one here. This is one of the faces of the box. Then some more terminology, of course, is the vertexes or vertices. Is a corner of the box. Same picture. Well, that was a rectangle, you know that. And I'm going to add the depth because there's actually 8 total. I meant to write 8 total. There are 8 total vertices on a box. So we'll highlight them now. Yeah, it's a lot to draw. And then last definition for a box is the edge. There are, this is the line that connects 2 corners. And there are 12 total. Draw one more time. That's a lie. We're going to draw it again. Just not for definition purposes. So any of the edges, like the edges are the edges. If you get my get what I mean. These things here. Twelve edges total. 4 vertical ones, and then 8 horizontal. 4 up top, 4 on the bottom. And the last thing is that a cube is a special type of box. It's a box where all 6 faces are squares of the same dimension. So cube is that has that requirement. It's basically the square equivalent, like a box is like the one-dimensional analog or the two-dimensional analog of a box is a rectangle. The two-dimensional analog of a cube is a square. So it's one of the nicer ones. So all cubes are boxes, but not all boxes are cubes. So when you move on to three-dimensional, you now have a different measurement to deal with, which is volume. The amount of stuff that can be fit into this object. So we're going to talk about volume and surface area. So we're going to write them down. We're going to write down the formulas for them with a box to follow along with it. And then dashes. That doesn't look perfect. Can't handle that. All right. So we typically measure them as length, width, and depth or height. So call the bottom one length, which will abbreviate L or capital L. And then width is on the side. And then height. So you don't really have area anymore. You have surface area. What will be required to paint all the sides of the shape? That is the surface area. Is if you were to cut it up into all the different pieces and lay them flat and add up those areas, that would be the surface area. So the volume, very, very nice. It's length times width times height. But surface area, which I'm going to abbreviate S. I don't know why I didn't write vol, like, should write this prettier. Volume. And then surface area is a little challenging because every single side has different measurements. Notice that the side ones here, if I'm to look at just this rectangular bit, that has a side that is width times height. Whereas if I do the one directly in front of us, this one here, that is height times length. But there's two, like there's two opposing ones. There's two opposite ones. So the surface area formula, usually abbreviated with an S, is 2 of length times width plus 2 width times height plus 2 length times height. And so the justification there is that you're just adding up the area of each face. So you can memorize this formula if you want to, or you can just realize that you're adding up the area of 6 different rectangles and do that. Either way is fine, but that is the formula for those. Okay. So those are the formulas for volume and surface area. So I'm going to do an example of this. How to use this, and it's a real life example. So See's Candies needs to fill a box with 200 inches cubed worth of chocolate. A dummy in the purchasing department requested boxes that were 4-inch by 5-inch by 8-inch in size. These boxes were 4 by 5 by 8 without knowing how much chocolate was in them, without knowing if they would fit, if they would hold the chocolate. Will he get fired? I.e., will the boxes be large enough to fit the 200 inches cubed worth of chocolate or not? Because he just bought a bunch of them without even testing it. So we're going to see if they can actually fit it. So we just need to know the volume. So volume, color, V is equal to length times width times height. Now, any of these, like, depending on how you set up the box, it could be that one of them's like, you can just flip the box on its head and then you've got different measure. Like the length is now the width, width's now the height, whatever. So it doesn't matter which one you choose. I'm just going to make length 4, width 5, height 8. And so this should be 4 times 5 times 8, which ends up being 160 inches cubed. So the box was not big enough. He's getting fired. Now the bonus question. So they're just going to have to proceed as normal. They're just going to have to just dump out the rest of that chocolate. And that's dump out 40, or just make the boxes smaller and charge less. But it costs $0.05 like, so 5 cents per square inch of wrapping paper. How much will each box cost in wrapping paper? That doesn't make any sense the way that's worded. How much will it cost in wrapping paper expenses? Square inch is kind of a good giveaway that this is dealing with area, right? Because area is measured is two-dimensional. If it's talking about cubic inches, then we'd be talking about volume. But we're talking about the things that are going to be wrapping all the sides. So we need to use this. We need to first find out what the surface area is. because it's telling us the price per square inch of wrapping paper. If we don't know how many square inches of surface we have, then we won't be able to solve this problem. So we need to find the surface area of the box, which in this case, the surface area is 2 times the length times the width plus 2 the length times the height plus 2 length or width times the height. And it doesn't matter which one you put which, as long as they're all consistent. So this should be, so let's just make it so that the L is 4, the width is 5, and the height is 8. So 2 times 4 times 5 plus 2 times 4 times 8 plus 2 times 5 times 8, which ends up being 184 inches squared. So we need 104 inches squared of wrapping paper. And recall, so it's $0.05 per inch squared. That's a unit fraction. That's a conversion factor. $0.05 for every 1 inch squared. So we're back to section 1.4. We're doing a unit conversion. We start off with 140 inches squared. And luckily for us, we only need to do 1 unit conversion. We want to cancel the inches squared. Then down bottom, 1 inch squared is $0.05. The inches squared cancel. And now our measurement will be in money, which is exactly what we're trying to find out. We're going to find out how much it costs for this situation. So 184 times 0.05 is $9.20. That's a lot in wrapping paper. This is apparently they're going the way of Apple in their packaging, charging you $80 million just for the packaging. Don't get me wrong, it's pretty. It's pretty when you get that box and it's all pristine, but like it's unnecessary. And now it just takes up space in my house. So, okay, any questions on that? Last one is next thing is cylinders. And there are many other besides boxes and cylinders. There's pyramids, there's spheres, prisms, all those things. They all have very, very nice formulas. We are only going to talk about boxes and cylinders, but there's plenty more out there if you want to know. But a cylinder is a tube with circular end caps. A cylinder is a tube with circular end caps. If I wanted to be very, very particular, technically speaking, that's a right cylinder. Is that situation? There are plenty of different cylinders that aren't that perfect shape, but that's what our book classifies it as. And so what you're going to do is you're going to make an oval. And then you're going to take that oval and then draw 2 vertical lines down beneath it. And then, if you already know how to draw a cylinder, by the way, feel free to. And then you just kind of make a rounded bottom. And then you add a little bit of depth. And so you have a little line stemming out from the center. That's the radius, which we denote R. You could also have the diameter, but I think the radius is just going to be sufficient. And then you have the height of the cylinder, H. And so for volume, for the volume formula, it's going to be V is equal to pi over pi R squared H. And that's kind of interesting, isn't it? The area of a circle is pi R squared. And so we're just taking pi R squared and multiplying it by H. It's actually like, so a cylinder is basically taking a bunch of circles and stacking them up until they reach a height of H. And that's why the formula is pi R squared H. Pretty cool. Surface area, on the other hand, is a little more daunting. And would you guys like to see the reasoning or just want the answer? The reasoning, absolutely. So the surface area formula is that S is equal to 2 pi R squared plus 2 pi RH. That's the formula. And please don't bother memorizing it. It's not that necessary. You can definitely use this like a little cheat sheet of the different area formulas. But let's look at a picture of one to figure out why. Once again, you have your radius, R, and your height, H. Radius, R, and a height, H. So when you've got a cylinder, if you want to find the surface area, you've got the two little caps on top and that tube in the center. So imagine if I were able to cut this up, I'd break it up into 3 pieces. I'd break it up into a top circle, whose area is pi R squared, and then a bottom circle, whose area is also pi R squared. And that's where that 2 pi R squared is coming from. One circle up top, second circle down bottom, so a total of 2 pi R squared from the top to the bottom. And why then would be that little piece, if I were to take that sheet of paper, where's that 2 pi RH coming from? If I were to take that piece of paper and snip it at one spot vertically, I could roll it out into a piece of paper, like a flat rectangular piece. And the height would be H. And the width. Remember, this thing was created by being on the outskirts of a circle. So when I unravel it, the width is actually the circumference of that circle. So the width is 2 pi R. And hence the area is length times width, or height in this case. So 2 pi R times H. And that's where it's coming from. So you have the 2 little circle top and bottom pieces. That's where you get that 2 pi R squared. And then the area of the middle section, this piece right there, is going to be 2 pi R H. So enough time to do the last problem that I want to do here. a Pringles can has a radius that is too small for the average human hand, radius of 3 inches, and a height of 15 inches. Find the volume and surface area of the can. Find the surface area and volume of the can. Serving it forms a perfect cylinder. And we're going to use 3.14 for our pi approximation. I mean, we could draw a picture if we want, but we already have everything we need. We have the radius is 3 inches and the height is 15 inches. So the volume is pi r squared h, which in this case, that would be pi times 3 squared times 15, which should be, we're going to use 3.15. We're going to use 3.14 here. So 3.14 times 9 times 15 is 423.9 inches cubed. 423.9 inches cubed. And then for the surface area, it's 2 pi r squared plus 2 pi r h. So that's going to be 2 times 3.14 times 3 squared plus 2 times 3.14 times 3 times 15. Using that, plugging that in my calculator, 2 times 3.14 times 9 plus 2 times 3.14 times 3 times 15. You get, did I do something wrong? I'm getting a different answer than what I normally get. 339. Is that what you guys get? I don't know why mine's. Oh, yeah, that's why. I make sure I didn't write this wrong. Okay. No, I put it into my calculator wrong. So I get 339.12. Yes. And that will be our last answer. I'm sorry to keep you guys a little late, right? Oh, no, not yet. Not yet. 339.12 inches squared. This is an area measurement, so it's going to be inches squared. Okay. Any questions on that?
Yeah, volume is cubed.
The volume is cubed, yes, because there's 3 dimensions that are like length, width, and height. All right, guys, that will be it for unit 1. We'll come back on Monday and kind of do an overarching problem or 2, and then we will start unit 2 next week. Okay, guys? Hope you have a lovely rest of your day and a lovely weekend, and I will see you guys on Monday. If you have any questions, feel free to email me. Well, I'll see you then.